And so the goals for this lab are first to break wind down into its individual forces and determine how those forces affect the wind. So let's do it. So first off, what is wind? If I were to run into you in the street and just ask you randomly, hey, what is wind? What would you say? Well, what I would say, and a good definition, is that wind is air in motion. And as such, it's subject to Newton's laws of motion. And there are 3 of these laws. We're not going to really worry about the third one, but the first 2 are really crucial. The first one is what's called the law of inertia. And the law of inertia simply states that an object that's at rest stays at rest, or an object in motion stays in motion, unless acted upon by a net force. What this means is that if there's no net force acting on something, it's just going to keep doing what it's doing. Now, we don't usually see this a lot here on Earth because there's so many different forces that are at play. Let's say you're at a baseball game and the pitcher throws the ball. Eventually that ball is going to stop. Even if a catcher didn't catch it, or even if it just kept traveling, gravity would be pulling it towards the ground. Air resistance from the air would cause it to slow down. There are many different things that would make it slow down. However, again, if an object's at rest, it would stay at rest. If an object is in motion, it would stay in motion unless there's some net force acting on it. Now, with that said, this net force can actually be a sum of individual components. So there may be many different forces acting on something. So for example, with the baseball, I mentioned the drag from the wind, or the drag from the air slowing the ball down. You can have things like gravity pulling the ball down. If the ball is rolling, the friction from the ground is going to slow it down. And all of these individual things add up to a net force. And that net force is this sigma F over here. So sigma just means sum, F means force. And according to Newton's second law, the net force on an object is equal to the object's mass times its acceleration. Now, what does that mean? Well, if we were to assume, and then the third law real quick, every action has an equal but opposite reaction. That's how thrust works. But let's go back to the second law now. If we were to assume that the atmosphere's mass stays even, that it stays constant, that it doesn't change, then that actually means that the net force is only affecting acceleration. And so forces act to accelerate the wind. And saying that the mass stays the same, that's what's called conservation of mass. I'm not going to talk a whole lot about that here. Just the idea is that we're not going to worry about mass. We're only going to worry about acceleration. And so forces act to accelerate the wind. And when I say accelerate, what that means is that means to speed the wind in a certain direction. Either ahead, that's speeding the wind up, behind, that's slowing the wind down, or turning the wind. So basically, forces act to accelerate the wind. Now, with that said, when talking about winds on the surface of the Earth, and in the next activity we'll talk about upper level winds, but near the surface of the Earth, there are 3 key forces that act on the wind. And the 3 forces are called the pressure gradient force, and that's caused by differences in pressure. So all that high pressure, low pressure stuff we've talked about before, that is all important because the pressure gradient force actually is what kicks off wind. Now, once wind begins to accelerate, the Coriolis force then begins to turn the wind. And it turns it in a very set direction. Here in the northern hemisphere, it turns it to the right of its path, in the southern hemisphere to the left of its path. And I'll talk about that more in a few moments. And then finally, friction, really only important in the lowest 1,000 meters of the atmosphere. But what it does is it slows the wind down. So pressure gradient force moves the wind from high to low. Coriolis force changes the wind's direction. Friction slows the wind down. Now let's talk about each one of these just in a little bit more detail. So let's look at this very simple weather map. These black lines, these are isobars. And I'm sure you remember those from that infamous Lab 1A. Isobars are lines of constant pressure. And they're useful to help identify a predominant pressure pattern. And in this case, we have a point A, which happens to be on the 1,004 millibar isobar. Above it is the 1,000 millibar isobar, and below it is the 1,008 millibar isobar. Because I don't feel like I'm holding any surprises here, I'll just tell you that as you're traveling up, let me go back real quick. As you're traveling up on this map, as you're traveling up, pressure is decreasing, whereas if you're traveling down, pressure is increasing. Now think about this. Let's suppose that there was air at point A. What direction would the pressure gradient force move that air? Well, as we've already mentioned, the pressure gradient force is simply the force that moves the wind from high to low. So high pressure's down here and low pressure's up here. This force, or this point, would be pushed further up. It would be pushed towards low pressure. So the idea here, we have low pressure up here and high pressure down here. And the pressure gradient force is moving the wind from high to low. Now with that said, as the wind begins to accelerate, which is what the pressure gradient force is doing, it's accelerating the wind, it's going to then begin to feel another force acting on it. And that next force is what is called the Coriolis force. And the Coriolis force is caused due to Earth's rotation. So it's because we are living on a big globe that is rotating. And what this does is, because the Earth is rotating, that actually causes the wind's path to move relative to the surface of the Earth. That actually deflects the wind. And what I really want you to know is that the Coriolis force turns the wind to the right of its path in the northern hemisphere, to the left of its path in the southern hemisphere. And actually, the textbook has a really good demonstration on how this works, and there's actually a video demo that I'll include in the comments as well as on this assignment. I didn't do it, so I can't take credit for it, but it works really well. And basically, the idea is that if you are moving in a straight path, but what's beneath you is rotating, that's going to curve your path. And that's exactly what the Coriolis force does. And again, the way that it works is it turns you to the right in the northern hemisphere and to the left in the southern hemisphere. Now, one other important thing about the Coriolis force that I haven't mentioned yet is that the Coriolis force is proportional to the speed of the wind. Meaning the faster the wind, the stronger the Coriolis force. The slower the wind, the weaker the Coriolis force. In the upper atmosphere, the pressure gradient force and the Coriolis force are the only two things that matter. And what actually happens is, as the wind is accelerating due to the pressure gradient force, the Coriolis force is also intensifying. Eventually, an interesting situation happens